let's get started. So today's goal would be to finish this topic, ANOVA, and then we will work on regression for the 4 to 5 class, and then you'll be the review of the past papers. Basically what we learned today will be how to execute the operation of ANOVA in Excel, the one-way ANOVA, and then we'll go to two-way ANOVA. And mainly it is, as we said, it's just an operation of F-test, which is an extension of the two-sample t-test here. Okay, so let's quickly review the one-way ANOVA. Then we just quickly jump to the two-way ANOVAs. Okay, so one-way ANOVA, to remind you what it is you have a bunch of data, and each observation we have a groupings. Okay, and the grouping by itself has no, usually not, is a nominal variable. So you really can't say too much about the relationship. And if you want to consider the grouping has some relationship, that will cover in the regression, right? Regression, in those cases, the grouping will make sense. But now we are not saying the age group, although we divide them into 4 different parts. We are not trying to say how old you are may affect your variable X. So that would be the thing we try to see. But instead, we try to see if there's difference between the age group. We're not trying to explore how they're related. Okay, so the main thing we try to do is to try to see if different group have different little different group mean. Okay, so the data you have is each one will end out with together with the groupings. Okay, and this usually that is collected from your data set, right? And then that usually we group them by a list where you would put them in the matrix form, right? This is the way, the form that you will use it, and we will use it in our Excel. This is the form that will be used in our Excel. Later you will see. Okay, and the main idea is we have some normative assumption which said each group actually is a bell shape with the same variance. Okay, so the key here we have to work on is the equivariance assumption. Okay, this is a classical model, and the only difference between this different group is only the group mean, not its variance. Okay, so that is the key assumption that drive the model, because this is the special case of t-test, right? Remember t-test in two-sample one, we have a special case where the variance is the same, and that is the extension of this to multiple group. That is what we're working here. And you probably ask what happened if they have different variance. That is beyond the scope of this class. Okay, it can be done, but it's not something we are working on. Okay, so if you have the bell shape, you can decompose in 2 parts. One is the constant mean part, one is the bell. Okay, so the main idea is if this is the case and you go back to here, you can decompose it into the error term, random term, plus the constant mu. Okay, and if you write in this way, you can always write down what is a grand mean, right? It's the average of all the group means, and you can define the treatment effect to be the difference between the group mean and the grand mean. So that is the one thing. And the next we would say is we can estimate mu and mu I, right, according to the sample counterpart, right? The grand mean is just averaging all observations, right? It simply means your data, right? It just if you look at data, if you try to get all the number and average, then give you the mu, right? If you're just averaging single column, the first column give you mu1, right? If you try to average the second column, will give you mu2, so on and so forth, right? Until the last column, which give you the mu(n), right? And you take the difference between mu1 and mu2, right? Say alpha I will be mu1, maybe 1, right? Minus mu, right? And we try to see if the ANOVA is asking if all the mu's are the same, or the alpha I, what's called treatment effect, is 0. Okay, so that is the main idea behind. And the way we proceed the test is to use the F-test. Okay, and why is it F-test? Because you can use different measure of sigma, right? The main idea behind is you can measure the variance. There are 3 ways to measure the variance sigma, right? Under the null. Under the null, actually, all of them have, remember, under the null, right? So these X bar, right, have mu indeed, right? You remember Xi, this bar, also everything has mu, okay? So if you try to look at this problem, you compare this to the this one, the estimate, right? SST, okay? That, I mean, of course, MST, of course, right? If you do SST over n-1, right? This is an estimate of sigma, right? And also, if you also can do this guy, right? The MSW, right? Which is the SSW over C-1, because they're, oh, sorry, this M-C. Okay, and this is also a measure of variance, right? Minus C because you measure C number of sample mean, right? Because you have estimate X1 bar up to X bar C, so that's why minus C. And you also can measure this by MSG, right? Which is SSG minus C minus 1, because there's a C X bar, right? And then you estimate this guy. So that's why you have C minus 1 degree of freedom. Okay, so there are 3 ways to estimate sigma, okay, under the null, right? And even if you're under the alternative, right, this is still, even the group have different mean, this is still a good measure of sigma, right? Because even though they have different location, right, and you subtract its group mean, it's still a good measure of sigma, right? But the point is, MSG will not be correct, right? MSG, if the mean are different, right, it will not contain not only the sigma, right, the sampling error, but also the locational difference, right? So basically, this one contains sigma plus the location difference, right? The location difference is the difference between mu1 and mu2, so on and so forth, right? Oh, sorry, mu1 and mu, right? mu1 and mu, right? mu2 and mu, okay? If they're the same different, then it will be there, right? So that's why you are testing whether the MSG is bigger than the MSW, right? If MSG is bigger than MSW, then your null is wrong, right? Under the null, that should be the same. Is that clear why we do the F test? Is that okay? Because of MSW, right? We just contain the sampling problem, right? Sampling variance, right? And this variance will contain not only the sampling error, right, or called random error, but also if they're actually different, it will be reflected inside, right? Because you're checking how the means are different from each other, right? Because across group. So that's why that's the reason why you compare the two. Is that clear? Is that okay? I hope that is clear why you compare the two. Of course, doesn't really matter if you don't know, because you just basically running the program, right? You don't even need to calculate the SST, SSG, and SSW, because everything is given by the calculator, as I show you, right? So you don't really too much worry about the calculation, because everything just click and then come out. And but of course, it's good that you understand what's the formula behind, right? Because these are just three different ways to measure variance, right? And then you should expect one is bigger than the other if the null is not true, right? So that's why you have this one, okay? And as I said, this is a right tail test, right? So this is the example that how we proceed, right? So basically is we calculate the MSG and MSW, right? Remember, MSW is within, right? So it's just a proper measure of the variance of the random term, but MSG might contain the locational difference between the mu's, right? So that's why you divide the MSG over MSW and do a right tail test. Of course, if you want to do a left tail test, then you reverse the order, right? But very often, the notation is we do the right tail rather than left tail. So that's why we have the MSG over MSW, okay? I mean, there's no reason why you cannot do the left tail, the same thing, but the convention is we do the right tail, okay? So, and you can see this 2 times, okay? Obviously, this one is MSG larger than MSW, right? Looks like, if you look at this, should be F, right? Something like this. And it's like 2 point something, right? And this is, what's degree of freedom here? Degree of freedom is the number of group -1. 3 minus 1 is 2. Okay, this is 3 minus 1. And this is N minus C here. N is 12. C is 3. So it's 9. Okay, 2, 9. F 2, 9. And the question, there's 2 ways to do it, right? And first is you can do the p-value there. Remember, it's only right tail, right? It's right tail there. So you want to calculate this value. Remember, it's only right tail, so we just need to multiply by 2. So this area, if you do the Excel, will be 1 minus F this, and then 2.37, and then we put 2, 9, and then true. Okay. So that is the p-value, right? And then let's try in Excel. Actually, we'll give you this 0.155. Okay, let's actually do it. Okay, let's actually go to Excel and show you the p-value actually is more than 15%. So let's actually do it. 1 minus. Why 1 minus? Because you're clicking on the right hand side, right? Because Excel gives you the left hand side, so that's why you do the 1 minus. Okay. So that is exactly what we'll write down the formula there, right? Just like the dot there, there's a p-value there, right? And you can also do the critical value method, right? Which tells you the F inverse. And if the right-hand side is 5%, the left-hand side will be 95%, right? And degree of freedom will be 2 and 9. Okay. So you can see the if you try to work out the critical value, that will be here. Okay, this is 4.2. Okay, so which means we do have we can't really reject it. Is that clear? Is that clear why we can't reject it? It is because of the fact that the value is not within the critical, it's less than critical value. Right. So, and let's go back to here. Okay. So that's why this is the value. We can't reject it. Okay. So what does that mean? It means that the three groups the group mean are not the same, not different. So we don't need to treat them differently, right? Suppose there's a data of, I don't know, 3 different shops, the sales, right? And in that case, we don't need to carefully design how to work with these 3 different stores, right? Or this is your HR, these are the sales they did, right, last month. And you figure out that actually there's no difference between the 3 guys right? Then probably you would not try to give special bonus to 3 of them. Maybe you treat them the same, right? Unless you think out one guy is so stand out, you want to give bonus, right? So that is the idea here. Is that clear what it is going on there, right? So let me show you how we can do it, everything quickly in the Excel add-in. Okay, so that will make our life easier. Okay, so what I'm going to do is I just prepare Excel. Okay, maybe it's okay to change here. So let me create a new file which contain the let's call this file ANOVA add-in, which later I'll upload by the end of the class. Add-in, and today's day is 16th of November. Okay, so let me do it is by click out the data there, right? I have group 1, group 2, and group 3. The data I have is 1, 1, 2, 4, and 3, 4, 5, 8, and 2, 4, 5, 9. So what I'm going to show you here is you can also do it beside Excel. You can use any other software. But what you would do is to do ANOVA. It will give you all the answer immediately in one single click. So you will see everything will become way simple because of the fact that this is standard calculation that well, we can really do it very quick. Okay. So again, what we'll do, we'll use the add-in package from the data. Okay. And here it's not loaded, but if this is your computer, it should be there. Although many of you are using the Mac, but currently still in the business world, we still have Windows. Okay. So unfortunately, you probably have to understand how Windows works, right? Because that's why my slog is still have Windows, right? And you go to options and you go to add-in. Okay. Although some of you may say, why use Excel? Because you have Python, you have C, you have many software, but unfortunately, business world, I mean, currently still use Excel in many cases. So your boss probably will appreciate if you use the tool that he knows very well. Okay. So the data analysis is here. Okay. So, but I mean, the same technique same function should appear in your own Mac. That's not be issue. So it's click data analysis. Okay. And you go to the very top. That's called the ANOVA single factor. Okay. Single factor means it's one way ANOVA, right? Remember, factor is mean grouping. Okay, one grouping. So click OK. And then you will see there's actually very simple. We just tell them what are the input of the data. Okay. And here for us, it's just only first three column A up to column C. Okay. And the data you are grouping is grouped by column rather than row, because each group is a column. So that's grouped by columns. And since we have label in the first row, okay, that's G1, G is not to be used. Okay. And alpha, as we said, we always use 95%. Okay. Of course, if you like, you can do 1%. That is only important for you to do the critical value, right? The p-value doesn't really matter anyway. So if you are p-value, a guy, as actually most of us do look at p-value, so doesn't really matter the alpha you input there, right? So that's now the left is just you tell them where to output. Usually I just output to the next to this because we don't have a last data set. Okay, so that is okay. And so you will let me get this up, maybe it's easy. Okay, so the core of the one-way ANOVA is you should be able to understand every single thing here, right? And you should know how they're related. Okay, and here count is very simple, just how many of those, right? The sum is very simple. Sum is just adding this up, right? And average is averaging the group. Variance here is the sample variance. Okay, just note that the sample variance divided by n-1. Okay. So now here come to ANOVA. I think ANOVA is something we cared today, right? So what is this SS, right? By guessing, you would know this is going to between group is SS. G, right? And you can check your handout. It's actually the number that covered there, right? This is SSW, right? This is SST, right? And SST have degree of freedom with n-1, right? What's n there? We have three group. Each group have 12. 3 is 4. Then n is 12, right? And also we have a degree of freedom of group. This is C-1, right? And where how many columns here? C is being 3, right? And what is this number here? Right? This number is n-C, right? And it's being 12, C is being 3, so it's 9. Now, what the next, look at this guy. Probably you can guess this is MSG. MSG is just SSG over C-1. So give you 12 over 2, give you, 12 is coming from 24 over 2, right? So it's just basically column F over column G. Right here, we also have the same thing here. Right, this is basically the MSW, which is SSW over n-C. Right, so it's 46 over 9, which is 5.55. Okay, and then the next step would be, okay, look at F. F is what? F is the same as what we teach in the class, right? Is the MSG over MSW. So it just H this over this, right? It's 12 over 5.11, right? And then you can calculate the p-value, which is same as what we found, right? It's 15%. So you can't reject this or X0, right? Which is X0, which is saying that the three groups have the same mean. Okay, so you can't reject it at 10%, 5%, or 1%, regardless of which one you use. Okay, is that clear? So this is the most central thing, right, for the one-way ANOVA, because at the end of the day, this is what you are doing to do, right? You are not going to calculate anything, but you need to learn how to read complete output, right? Actually, when we learn the hypothesis testing, we just do it by hand, right? But increasingly, you will be using software, and that's now we're doing how to read the output. And it's important whenever you're trying to learn a software, you need to know what is the meaning of each output there, right? Just not, I mean, it's okay not to remember how it comes about, but at least you know what it is, right? Otherwise, you don't know what's going on, right? There's a black box there. At least you need not know how the black box is being run, but you need to understand what black box gives you, right? Otherwise, these days it's very difficult to survive as a data scientist, right? Because you just how to run the program, how to run the package is going to not give you a lot of competitive edge, right? Because recently, you know, more than 10,000 of workers on high tech has been laid off, and many of those are basically data scientists, right? If the data engineer, right, which create this kind of program, you will still be there, right? But that is the people who actually from computer science, right? If you're a data analysis or data scientist, then probably if you don't want to be laid off, you need to know a little bit more, right? Just running the program will not get you too far. At least you know how to combine and work one more. But anyway, it's not my job to talk about those things, but comes out, just a good reminder to many of you, because many of you have a mindset this class is not important because there's only class for statistics for your program. But these days, it's very hard to make a living if you don't have a special edge, right? And anyway, I should not talk about discouraging news for you, but anyway, but that happens, right? Is there a question? Okay. If no, then I erase this. I go to two-way ANOVA. Is that okay? Let me go to two-way ANOVA there. Sorry. So I hope you would appreciate why we study one-way ANOVA, right? And we go to two-way ANOVA, and probably you would ask what it is, okay? And by two-way is rather simple. Let me go to the definition directly, then probably you will see what it is, okay? And I'll give example. So what it is instead of each data have one grouping, you have two groupings. That is called two-way ANOVA. So what it is, let me give you example, okay? Suppose in the one-way ANOVA, right? Remember the example we have is we have this example is we have example we got is we have the one with X1 and G1, right? This is data, okay? And the example we give here is, say, X1 may be the GPA or the income they earn after they graduate for the CHK, right? And the grouping can be, say, college, right? Which college you are looking in, and then you want to see whether college affiliation of our undergraduate, do they make a difference, right? Is it, say, Chongqing College student going to make more than New Asia College, or the United College has earned more than the New Asia, so on and so forth, right? This is possible they earn more because the alumni is different, right? So maybe the old colleges and earn more, right? Or Chongqing College earn more because they have better alumni connection, right? It's possible. Right? A new college may earn less or maybe earn more, depends on what kind of information you have, but it's possible they're different, okay? So in this case, each student, we only care about one thing is affiliation of the college, right? But sometimes you get the data, say in each student, besides the college affiliation, one also very important, this is college, right? For the first one, we all may also care about the second thing, which is the faculty they are in, right? Is whether they are, the example of this may be whether they are in the business school, right? Whether they're in engineering, right? Whether they're in art, right? That's another thing, right? The college can be, say, NA, right? CC, SC, right? UC, and so on and so forth, right? So for each data observation or student, right, in the data, actually can be characterized by two grouping, right? Or we call two factors. There's one factor is being college, the other factor is being faculty, right? And you can see these two factors are, by definition, is independent, right? Because that is usually what it means independent, right? If they're dependent, then probably two-way ANOVA is not very good idea, but still you can do it. But by definition, any combination is possible, right? And in practice, why we have this is it's coming from experiment, right? It's coming from the idea of suppose you're a farmer, right? You can change one dimension, say you grow a crop, you can change different level of sunshine, right? And which is A. B may be different levels of, say, fertilizer they use, right? Then you want to see different level of the sunshine and different level of fertilizer, which combination is going to give a difference, right? Or any different levels will make a difference. And probably you would wonder why we need a two-way, right? Because you can just treat them as one way by combining the two, right? You can call NA business school as one group, NA engineering is another group, right? Why we need two-way instead of a very long big one way? Do you see what I'm saying? Because one way is many groups, right? We don't have restricted grouping, right? Why we have to care about combination of the two grouping? The reason is we want to see if there's a magic or the chemistry between the two groups, right? Maybe different sunshine level have no impact, or different level of fertilizer no impact, but a particular point of sunshine and particular fertilizer level actually make the magic, right? So it's the idea of 1 + 1 not equal to 2, right? It's a synergy, right? It's a combination, a special combination will do the trick, right? So go back to the student, right? Probably different college have no impact on student GPA or income, right? Or different faculty may not make much difference, right? But it's possible that, say, for example, due to history reason, for arts and social science student who graduate from New Asia College, actually is better in terms of GPA or in terms of income, because you get a better training under the history of New Asia College, right? Or if you are from the religious school, right, the religion study, and probably Chongqing College, student from there actually is doing better, right? So there is a kind of the combination that make it works, right? Or you're athletic student, then probably maybe you are from the Seoul College, it's better because it's far away from the campus, you walk every day. So it's possible that would happen, right? So that is another thing that will comes out. But the main idea is because of you divided into two groups that then the combination of different groups can probably would make a difference. So that's why we talk about two-way ANOVA. And of course, probably you ask, can you do more than two-way? Yes, you can do more than two ways, but that is not the concern of our class. Okay, you can do three-way, four-way, five-way, as many way as you want, but that is the math will be very complicated. That is not the concern for us. So so we have C different number of group A and R number of group B. So actually C means column, R means row. You will see R means row. Okay, C stand for column. And later you will see when we write down the matrix why we call C and R, but that is not my notation, the standard notation in textbooks. Okay. So because two-way ANOVA is very complicated, for our purpose, we focus on the very simple setup, which we did not impose in the one-way ANOVA, but we imposed in the two-way ANOVA. Each combination of factors have same number of observation, which we call equal number of replicates, which is also the special case, also the case that you work for Excel. Okay, Excel only work for this kind of situation. What does that mean? It means that look at NA student that from business school, say you have 10 students from the data. Okay, you also have 10 students for NA engineering, 10 students for NA art student, 10 students from CCB school, 10 students from CC College engineering, 10 students for CC College art student. Okay, so each combination of factor are the same. So that's why it's n prime. So that's R times the n prime is n. Okay, so total number of observations is to n. Okay, so why this weird notation? I follow the book. Okay, just to make sure that you when you read the book that it's easier to see. Is that okay? Is there a question before we proceed? So is the setting clear? So I mean, maybe it's easy to see the data you have, okay? This is the data form usually you get from the survey or you get from the database. So what you can see here is each row is an observation, okay? Each row is observation. Say, this is the, say, GPA of the first student, okay? And this is his college affiliation for maybe NA or CC, right? Or SOR, maybe UC, so on and so forth, right? And the last item, right? Maybe his is faculty, maybe business school, maybe I don't know, engineering, right? I don't know, maybe education, and so on and so forth, right? So each observation will have two groupings, okay? So this data, right? And probably if you do a survey, right? This is 3 separate questions, right? Question 1 is what's the GPA? Question 2 is what's the college? Question 3, what is your faculty? That is the 3 question there. That's how you collect this data, okay? Is that clear how you get this data? Because that's how you collect those. And you can see this is the data people would call a narrow data or long data. And because this is very long, right? Because each entry will have one. Okay? Is that okay? Is that clear? If that's okay, let me talk about this matrix and then we have a break because I think it's almost time. So here is this data is nice, okay? It's nice to see, but this data is not convenient to describe, okay? So that's why when you look at the formulas, that's how we make it. And this also we call the matrix form, okay? The matrix form, we will have for each data, okay? We will have a phi number there, okay? Okay. and we call IJK, right? And generic is IJK, right? So first I is telling us which, in our example, is which college they're in, right? So, and we use 1, 2, 3 up to C, right? So probably in your mindset, 1 maybe refer to NA, right? 2 maybe refer to SAW, 3 maybe CC College, 4 maybe UC, right? And 5 maybe whatever, right? And J, what is it? J is faculty, if in our example, right? And in that case, 1 may be B school, right? 2 may be, I don't know, engineering. 3 may be education. Okay, so on and so forth. Okay, and you put this number to that, it's just for convenience, right? I mean, there's no difference when you put what number you put them. Okay, and the last one is K, right? What's K? K is the probably you can call the serial number. Okay, it's basically the first observation in that particular grouping, right? Say K1 means, suppose we talk about this one, X111, which is the first observation that is the NA student in business school. Is that clear? If you have, say, for example, X223, so this is the third observation you get for the student who is in the SAW College and is engineering. Is that clear? What the setup is? Okay, and I'll talk about the model and the thing after the break. Okay, I hope this is clear. What is the setup, the notation, and then we will impose the bell shape on each group and do the same procedure. So you will see it's almost the same as what you see for the one-way ANOVA. Okay, but in the meantime, there's a break. And if there's still a problem of how to do the Excel, let me know. I just go around to check it out. So let's have a 10 minutes break. So it seems like you don't have much problem. So maybe I cut the break 5 minutes short, then we can release you 5 minutes earlier. Okay. So if you don't object, because I don't see anyone in the washroom, and then looks like everyone's okay. So maybe I can just get it through faster. Okay. Is there any question before I proceed? No. Okay. So so this is the matrix form here, right? So as I said, this is a grouping of A, right? Just to carefully remind you after the break, right? These are, in our example, these are just college, right? It's NA, CC, so, right? In that case, right? And these row, okay, are just B's are just faculty, right? So maybe business school, maybe N with education, right? And here you can see this is the first observation from NA under business school, right? The second observation of N and the business school. right? So on and so forth, right? So you can actually see this is the data, right? And this is data that will fit into Excel, okay? So later you will see when you try to do Excel, this is a data structure that you need to input, right? And do remember that your data is not in this format, okay? And your raw data is the format like this one, right? And one of the question is how you can transform this to here. If you do Excel, I don't know there's a fast way, but you can do a filter function, right? And do copy and paste. Unless your data is super big, it shouldn't be an issue, okay? But if you handle a big data, then probably you want to use a dedicated software like, I don't know, R or Python to convert it. Maybe there's something Excel can do these days, but I'm not aware of that as of now. Okay. Is that okay? Is that okay? Okay. And if that's okay, then we go to the assumption here, okay? The assumption is exactly the same as what we see in the one-way ANOVA, right? It is the assumption we have is all of them are the bell curve, okay? So each observation is a bell. The only difference here is this bell, the mean will depend on potentially a much more finer detail. If you remember what it is before with this one, right? This is mu I sigma square, right? So, but now it's not depend on the group. The grouping is not just one. We have two ways of grouping. So that's why the bell shape is look like this. Is that clear? Okay. So, so we will take this part, we decompose it into 4 different components. Okay. So that is what comes to the next one. Okay. So which means that the mean of each group mean, actually is the sum of the 4 parts. Okay. First one is the overall mean, right? This is the grand mean. Okay. Which we'll define the next slide as the the grand mean is the mean that if you really don't care about the grouping, right? It's the mean that none of the grouping is being considered, right? That will be the mu, right? And what is alpha? Alpha is the treatment effect due to A, right? What does that mean? Say suppose mu is say NA and say business school, right? In that case, alpha I is the treatment effect of NA. So asking, being a New Asia college student, what is the impact on the GPA or, right? And beta, okay, will be the treatment effect of business school, okay? It's asking if you're B school student, what is the impact on your GPA, okay? And lastly, the last one is the treatment effect of NA and business school, okay? Being a NA and business school, do you have extra boost Okay. Okay, so that's why that mean actually combine 4 different elements. Okay. And is that clear? Is that clear? And we will define all of them in the next slide. Okay. Is that okay? So it's not probably not clear what are they. We will define now. And this is a new slide I add if you have an old version. So this is a new slide add. So what is the overall mean? It just simply means all possible groups mean together over how many total of them. All right. So basically just the mean of all group means. Right? Say mean of all group means. Okay. And this mu, okay. And we can also define what is group AI mean, which is the mu I dot, okay, which means that you look at the mean of the column I, so I suppose NA, okay, which means that you look at, say, this is NA college B school student, right? This is NA college education, right? So you basically look at all the NA student, okay, the mean of all the faculty, right? And this is I dot. Dot J means what? Suppose J is the, I don't know, business school, okay? And this is the, say, NA college business school, okay? At the end, this is the, say, UC college business school, okay? So basically, you look at all the colleges, right? There's a mean for the business school, averaging up for overall college, okay? So these are the mean, depends on some groupings, right? Is that okay? So basically, this is the grand mean and group mean, okay? And once you have this, then we can define the treatment effect. Is that okay for this one? So basically, just like the mean for B school, right? You just averaging all the B school mean over all the colleges, right? If you have the education over all the colleges. Is that clear what these two means are? Okay. Is that okay? No, okay. So let's it's good to take a look at this one. So if you look at this, okay, this is, what is it? The meaning of this is this data throughout the mean is mu 1, 1, right? And this data average actually drawing from mu R1, right? And what does that mean here is this whole column will give you mu 1 dot. Okay, so you calculate each data, right? And each data, the average is this mu 1. Okay, is that clear? But do note that we're not talking about data, right? This is the mu. So just hypothetically, what's data behind it? Okay, it's not about, it's the expectation, right? Average of this expectation, not exactly data. We'll talk about the version of data, but this is what it means, right? And similarly, we have, okay, this guy, maybe use other color, okay? This, if you average this guy up, right, that will be mu dot 1. Okay, is that clear? Of course, if you look at the overall, of course, the overall will be the meal, right? So if you don't care about it, it is drawing from meal. Okay. Is that clear? So if you each particular group have all the mean, averaging of all this mean give you this meal. Is that clear? And that's how you calculate the sample version. Later you will see. Is that okay? Okay. Now, that's how we define the treatment effect, same as what we do, right? If you look at the treatment effect of particular group A, which say is NA college, right? So it's just the mean of NA minus the overall grand mean, right? And if you want to look at the treatment effect of, say, business school, right? So focus on business school mean minus the grand mean, right? Gives you beta. Is that okay? Now, the last one is, I mean, the first two is nothing, but same as before, but the last one is a bit tricky, okay? So what you're going to do is look at how the particular group mean minus overall, okay? So, but this is not the end. The reason why is because you have to take away the single individual treatment effect, okay? So that's why you take the particular group mean over the grand mean, but you have to subtract the treatment effects for individual group. Okay? Because of this, because the effect have to be this impact and plus this impact, right? So that difference, right, have to be subtracted too, right? Basically just the remaining term, right? Because that you move this thing up, right? Or you move all three things term to the left-hand side, which going back to our assumption, right? Because that is how we define tau, right? If you remember, this is the function, right? Mu ij is equal to mu plus this, right? So that is this one, okay? And if you put what the alpha and beta here, just like the specific group mean minus the I group mean minus the J group mean plus the overall mean. So this is the most difficult to understand. If you look at the formulas, okay? Okay. And as you will see, two-way ANOVA is asking to see is the alphas are 0, betas are 0, or delta is 0, right? Because ANOVA, remember one-way ANOVA, is asking whether treatment effect is 0, right? In the one-way ANOVA, asking alpha is 0. So in our case here, we can ask more question is whether beta is 0 or delta is 0. Okay. So that are the three questions there. Okay. Is that clear what we are doing? Okay. It's asking whether the mean are different. Okay. Based on the grouping. Okay. So here is how we do the calculation. Okay. And let's not be scared by the summation notation. If you look at the data, it's very straightforward, okay? So let us read them, and then I will tell you how you can visualize it. That's very simple, okay? So this is what the first one means. I sum all the column, which means that I, in our case, is sum over all college, right? That's the summation sign means, right? I go from college 1 to college C, okay? And the next one is I sum over all row. In our case, we sum over all faculties. Right? Sum over colleges, over faculties, right? This is the second item. And here the last item is what? I sum over all observations. Okay, so for each college and each faculty, I sum all the observations and I do the N. All right. So what does that mean? Let's go back to here, right? Which means the following. It just simply means I just add everything up and divide by N. So that's X bar. It's very simple. I just completely disregard the grouping, right? There's no meaning of grouping. I just calculate the simple average of all data. Is that clear? So that is what it means, okay? So I hope you don't feel scared by the triple summation. Okay? Is that okay? Just basically add up everything divided by the total number of observation. So the second one, okay, is don't be scared, okay? It's the ith level of factor A, right? So just to remind you, this is just mu, measuring mu, okay? Here we are doing mu I, okay? What is measuring is, okay, very simple, okay? The green one is what? Sum over observations, right? And what is the orange one? Sum over all the faculties, okay? So give me a college, I sum over the faculty observations, right, of that particular college and divided by how many of them, right? So what does that mean in the diagram? Okay. Go back to here. Okay. It means the following, right? Let me erase this one. So if we're given the college 1, right? Suppose you're current this will be x1 dot. If you calculate average of these two, this will be x2 dot. If you go to the last one, this will be x bar c dot. Is that clear? So just all the column average. Okay, I mean that's same as the mu version, right? But the mu version is the actual thing, but this is the data thing. Is that clear? Now it's clear, then probably I don't need to write that down. You can see the analog. If I average the row here, you should expect this will be x bar dot 1, right? If I figure out this guy, this will be x bar dot r, okay? So it's the group mean, focus on just the our faculty, right? Is that okay? Is there any question? And maybe we can go back to the definition. Okay. This is coming from, right? You can see you are summing over all the colleges, right? And over all the student, right? For if you're given the faculty J, right? And you just sum over all the people in the college, right? Within the same faculty and then over all the student. Is that clear? Is that clear what we're doing here? Okay. So we have this and that, okay? So if that's no problem, we go to the very last one, okay? Right? It's the x bar ij, and as you would expect, this is going to give you an estimate of mu ij, right? What is it? It just basically give me the ij, I just add up everyone there and over n, okay? So it's very simple. look at data here, right? If I look at the red one, this will be X bar CR. This will be X bar C1. Say I have a red here. The average of this will be X bar 1, 1. Okay, is that clear how you can calculate this means of within? Of course, we get for example, but this is what it is. Okay, and if there's no problem, okay, is there any problem? How you can define all these 4 grouped mean? It shouldn't be a difficult one. Now, if there's no question here, let's go to example here, right? So to illustrate again how you can operationalize this, right? So how can you calculate this X bar? You just add up everything there. Okay, the average out, this gives you 4.5. Maybe I use the same color here. Okay, this will give you 4.5. Okay. And let's see how you can calculate the next one. How can this guy? This guy is the average of this, the first column. Okay, the first column. And if you want to calculate this one, this will be the second column, average of this, right? If you want to calculate why this is 5, it's just this guy. Okay, and if you want to know why we have this pain, is here. Is it clear how each one being calculated? Is that okay? And lastly, if you want to, I don't know, one of colors, I guess, darker red here, okay, maybe. Is it going to help? This is a good one. Red here, okay. And if you want orange, it's like this. If you want green, it's like this. If you want purple, like that. Okay, so that's how, I know it's very colorful, but I don't know whether you can read that. Is that okay? How each one being calculated. Stop a little bit and see if you have any question. Let me know if you have concern how to do calculate that. Is there anything I can help? Is that clear? How each entry can be calculated, all right? Is that okay? Any question about how you can do it? Okay, if no, then the rest will be easy, okay? Because all the calculation will rely on this means, okay? No question. So as we said, we try to ask whether alpha the same, beta the same, and tau the same, and we rely on F test, right? Because of how we can measure the sigma square. Okay. So let's look at this. It's just we have SST, SSA, SSB, and SSAB, SSE, and turn out to be this SST same as sum of all this. It's very similar to what we have, but okay. But let's see what is the SST first. Okay. SST is very simple. Okay. SST is simply, if you remember these three summation, okay? First one, you go over all the college, right? Go over all the college, all right? And then you go over all the faculty, okay? You go over all the observation. Right? Then what you do is you subtract each observation by the grand mean, right? So this is what you would calculate if you try to calculate the variance, right? You over n minus 1 will be the numerator part of the variance, right? If you really don't care about the grouping, right? If you calculate sample variance of this data, this is the numerator of that, okay? It's the numerator of the sample variance, right? If you try to actually forget the groupings, okay? So later we'll have MST, that will be actually the method we're looking at, right? And the next one is same as what we have seen. This is same as SSA, is same as SSG, okay? But MSG, but we focus on the A, okay? Look at what we're doing. SSG is between group variance, right? So look at this look at the group A, okay, and overall mean, right? So basically you just replace the observation by the mean of group based on A only. So you enter the college means, right? You replace every observation with college mean. That's how you do the calculation, right? So we place everything in the college. So if you look at how to operationalize this, is you go back to here, right? You just replace everything here, right? So the simplest thing is what you do is you look at this number here. Maybe I use the green color, right? This data, instead of putting this, you calculate the mean of this, right? X1 bar. And you forget about this number. You replace them by X1 bar. And do the same as you do in SST, okay? So that is the main idea how you do it, right? Just replace every observation by the group mean. So the column average, replace everything there. And the next one is the same, but you just look at B, so you just replace by B, okay? Look at the first item, the same thing, okay? There's nothing new there. Just go over all the observation, but instead of the column average, you replace by row averages. Is that okay? Don't worry, we will see the example and you will see how it can work, okay? Now with this, okay? And do note that this related to alpha I, right? If you remember, this is beta J. Okay? It's related to that, right? Alpha 1, 2, 3, right? Because this minus this is measuring the alpha I, right? And this is actually the beta J. Right? If you remember some estimate. Is that okay? And we will do the, okay? Did you remember this is exactly the case with we have tau ij, right? We have the each group mean, okay, minus the I group mean and minus J group mean and plus the X bar. So this is trying to capture the interaction effect, right? It's basically looking at ij minus I minus j plus back that thing that is capturing the tau, right? This is, if you look at the version, it's measuring the tau ij, right? And square, right? The first one is alpha I, that's the beta, then is the tau ij. Okay. And the very last one, we call SSE here, but this is just SSW in our old version, right? Because what we're doing is you take every data, but instead of the overall grand mean, you subtract it from the, oh, sorry, that should be no dot, sorry. That's okay, that should be no dot because I don't use dot here. It's just xij here, okay? So instead of the overall mean, but you just look at the mean of the particular group, okay? And turn out that may not be surprising, the overall variation is equal to 4 of them, right? So this is coming from the college impact, right? The college, right? And this is faculty, right? And this is college plus faculty, right? And this is random error. If the main idea is these 4, okay, are actually the measure of variance, right? If you divided by the appropriate degree of freedom, right? This 3 different way, right? And if there's no college difference, right? It should be this one must be no different from this one, right? Because you also have some error when you measure this one, right? So to be exact, I have some. To be exact, if you want, you have this plus the random error, right? Plus the error, right? And if there's no college difference, right? These 2 should be the same. If there's no difference by the faculty, these 2 should be the same. If there's no the joint effect, they should be the same. Okay. So what we need is to come up with a measure, right? How to measure variance based on this, right? This is same as what we see in the one-way ANOVA. Is that a question? Okay. So that's why it's very simple. Okay. But before we go to the simple thing here, let's show you how to calculate this SST, SSASB, right? So it's very simple. As you can see, SST is simply look at this 4.5. You go over every element, you minus sub 4.5. Okay. Give you 91. Is that clear how you get that one? This is a new slide I add because I think that would be more clear. Okay. But there's no change in your anything. Okay. This is just I add them. If you want, you can go to the updated version. I just put it there because I think it's easier. Is that okay? I mean, but I think you know how to do it, right? SST is like this. And similarly, you know how to do the SSA. Okay. SSA will be the same. You look at the 4.5 is still at the end. Okay. The only difference is because you just replace this guy by 3. So that's why it's here. Okay. That by 3. And then you replace this guy by its column average, which is 6. So that's why it's here. So is it clear how you do the SSA? Of course, as I said, usually you don't do this operation, right? This is given, the data will give you already, the software will calculate that for you already. So this is how you get 27. Is that clear? I just supplement this to your slide because some of you in the other section actually asked me how can we actually do it. I just put it there, but this is just a formula, okay? And is that okay? Okay. And the next one will be the SSB, okay? SSB will be, again, the same idea, okay? Here 4.5, 4.5 is here. Okay. The only difference, what we do SSB is we replace this by its row average is 5. That's why we have 5 here, 5 here, 5 here. Okay. And we also have replaced this by its column average, which is 2. So it's 4 here, 4 here, 4 here. Okay. Is that clear how we do it? So basically just replace with the SSB, just replace everything by the row average and do the same as you do SST, right? Same as you do standard variance. Is that clear? Is that okay? And as I remind you, you never do this, right? In practice, right? Because computer just quickly calculate everything out, okay? But I just show you the black box how you can do it, okay? Now, this is SSAB, okay? SSAB will be just a little bit tricky, okay? AB is, look at the last item, you plus this guy, is this here, okay? And look at the first item here, okay? This one is 4, okay? And you notice you minus 3 and 5, right? Because this is 5 is the column average, 5 is the row average. So that's why you minus 5, okay? That's why same for the thing in the same red, okay? And the next one is 5 is here. Okay. I do is 3, right? Yeah, I do 3 here. I think a typo here. Yeah, typo here. It should be. Sorry, it should be 3. Here is 3. Then this the average is 4. So it should be 3, 4. Okay, should be 3, 4 here. Okay. And yeah, just change this 3, 4. This is 6, 5. Okay. So that is how you can calculate this. Okay. I'm sorry for a typo, but I'll update it later. But that's how you calculate SSAB. Okay. So okay. Is that okay? I'm sorry for the typo, but is that okay? So now we have SSAB. Okay. Is that okay? So the last one is we want is SST. SST is really simple. It's just replaced by yes. So this group have group mean of 4. So that's why 4 is here. Okay. And this group have group mean of okay, typo again. So 1, 2 is 2. No, that's all right. Sorry. This is 2, 1 is 6. So this will be 6. Okay. I'm sorry. 2, 2, 2. Okay. So because that 2 is here, though this is 1, 2 is here. So that's why minus 2. Okay. So the last one is 6. Okay. So that's how you get 6 here. Okay. So that's how you get SSE. Okay. So that's how you get the number. Okay. I'm sorry for the typo. I will be careful. Okay. Now, once you have this, then we're almost done. We're almost done because nothing just blocking us because we know the different way to handle it. Okay. So first thing we prove this the thing, right? This slide is in your slide already. That one I just showed you how to do calculation. So turn out to be SST is equal to SSA plus SB plus SAB plus SSE. Okay. So as I said, you actually compare the MSA and MSE, MSB, MSE, MSAB, and MSE, which is defined in the next one. Okay. So SSA, right? Remember, is you try to look at the variance, okay, based on the college difference, right? Without regard to difference within college, right? And the same here is, this is the variance among faculty, and you just average, you just forget about the difference among colleges, right? And this is looking at the interaction of these two terms, basically taking away the things that is unrelated to that, right? And the last one is the variation, right, of the last guy, right? So basically, just maybe erase this, use a color, right? In some sense, this is what it's doing, right? This is looking at alpha, right? This is looking at the beta, right? And this look at the tau. Use the red one, right? And this is reflecting the overall thing, the sigma square, right? And you remember you have to have sigma square in each one, right? And you try to compare these two, right? The null hypothesis said this is 0, right? So you compare MSA and MSE, there's a F test, right? And you compare MSB and MSE, that is also F test, right? You compare this and this, MSAB, MSE is also F test, okay? So you try to see if alpha is 0, beta is 0, tau is 0. Is that clear? So that's exactly what we have here, right? You calculate MSA, MSB, MSE, okay? Once we are done, okay? They're actually here, okay? So the same thing here, MSA over MSE, okay? And this is just a right tail, okay? And this is, the only difficulties is to remember this C minus 1. And the degree of freedom is RC times M prime minus 1, okay? So that is that's a difficult part for you to remember, is this is the degree of freedom, okay? And same for MSB, okay? And MSAB are the same, okay? So I guess it's good to look at the example, okay? Because I don't see there's not difficulties here, because same as what you learn in the one way, okay? So look at the first one, okay? MSA and MSE, okay? And MSA is 3 times more than MSE, okay? So we may be hopeful there's something that group A would make a difference, right? So you expect this thing will happen, right? There will be F. Because of 2 groups is 1, because this is C minus 1, right? And how many data of it? So it's remember the formula is RC M prime minus 1, okay? And here R is 2, C is 2, right? M prime is 3. So 2 times 2 times 2 is 8. Okay. So the question is this 3 point is going to be big enough? All right. So that's the question. So you do this for the MSA, right? You do the same for the MSB and MSAB, right? And then the p-value turn out to be, how to calculate that, right? It's just 1 minus F dot this 3.732, and then 1 and 8, and then true, right? And turn out this is 8%. So if you use 10%, you reject, but if you use 5%, you don't, right? So in this example, that group A, grouping by A actually it will be meaningful if you use 10%, right? Use 5% is no, 1% is no, okay? So, and for the grouping of B and MSAB, actually we don't need to do anything, right? Because we try to claim this is bigger than this, right? But turn out even data doesn't show anything. You don't need to do anything, right? You must reject. You must can't reject it, right? Because we try to see if MSB is better than MSE, right? There's no way, because data show is actually less than, right? So you don't need to. We can just go home. Is that clear? Of course, you can do the F test, right? You can do the F test as I write down in the slide, right? But you don't need to do it, right? Because by construction, you don't need to worry about it anyway, right? Because we want this variance is higher than that, right? But it's less than that. We don't need to do anything. Is that clear? Is that okay? Okay. So maybe I hope it's okay. I just go quickly to the Excel. Although I supposed to give you a 5 minutes earlier, but I'm sorry. I mean, forgive me for that, because I don't want to keep it for the next week, because that's running the program. Okay. So I just very simple. I do a two-way ANOVA here. Okay. One way. Okay. And I do a two-way ANOVA. And you will see it is very simple. So I just A1 is here, A2 is here, maybe bigger. So I have 408, okay, 330, 558, and 945. Okay, and we have B1, 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 B2, B2, B2. Okay, so the data basically come from here. Okay, so I'm trying to show you. Okay, I'm trying to show you quickly how you do the ANOVA quickly. Okay, so you just go to data analysis, and go to the second one, ANOVA two-factor replication. Okay, replication. So you just click OK. Okay, and just tell them what's the input there. Okay, the input is from A1 up to C7. Okay, and how many data per row? Okay, we have B1 has 3 rows, B2 has 3 rows, so it's 3. Okay, so it's very simple, right? Just tell them what data set there, how many rows there, then you're done. Okay, alpha is 5%, but as I said, alpha doesn't really matter unless you want to care about critical value, right? So output range, you just put, I don't know, put there. Okay, is that clear how you can do this? Okay, and then you click OK. That's there. Okay, so here the first thing is the summary. Calculate the count, sum, average, variance. I think is you know how to figure out. But I think here is what we want to know. Okay, I think you should be able to see how each thing is there, right? So if you see within, actually you will see this is SS, this is SSE, this is a E, right? Or SSW in the one-way ANOVA, right? This is just a T in the it's different color. Right? This is just a T1, right? And this is just what? This is AB. Okay. And the columns, right? By construction, this is just A. And for us, this is just B. Sample as B. Okay. So you can see this is just, right? This is just SSB right? This is just MSB, right? Similarly, this is just SSAB. This is MSAB here. Okay. And this is just SSA, and this is just MSA. Okay. Finally, this is just SSE, and this is MSE. Okay. And the F test is just dividing each column, right, by the MSE, right? That's give you the L to F, and give all the P's, right? And that is all the F tests we have done, right? So I hope that's okay, and you should be able to understand every single entry here, right? Just to final remark, right? This is what? This is just R minus 1. This is C minus 1. This is, right? This is RC M prime minus 1, right? And this is just C minus 1 times R minus 1, right? And in this case, C is 2, R is 2, M prime is 3. Okay, so I hope you know every single entry there. Okay, so I will see you next week. So we're done with ANOVA, and the next 4 or 5 class we'll do regression. Okay, so the last homework will be released later. Okay, but not now because you have one homework already. So one homework is for hypothesis testing will be due next Friday. Okay. Okay, I'll see you next week. Have a nice day. Bye-bye.哦，呢個0.5，我係寫錯咗，我係寫錯咗，呢個寫錯咗。哦，呢個啱嘅，呢度合 P and P 錯咗。哦，唔好意思，唔好意思。因為有幾個全部。哦，唔係呢個係啦，呢個啱嘅，係呢度先話，呢個係。啊，唔該晒，我唔好意思 typo， 係啦。係啦，唔好意思，呢個0.5，唔好意思，唔好意思，你明得啦嚇 ，OK， 唔該晒，唔該晒。